It's a huge pleasure to be presenting this. It will be kind of a speed run because 5 minutes to explain this so that you understand is too few, but we'll try our best to get you excited about this. So why are hash-based proof systems important, okay? So they are used right now by many projects, and they have helped develop performant zkVMs that make developing provable applications easier, because now you have to just write ordinary code and something else is going to take the gory details of generating the proof and all that. So what are the properties that hash-based proof systems offer? First, we can work over smaller fields, which reduces a lot the overhead that we have in representing the variables. Then another advantage is we don't need any kind of trusted setups. There are like minimal security assumptions depending only on hash functions. And it's easier to generate recursive proofs because we don't need to do any kind of field emulation or elliptic curve operations, which are very expensive operations to perform. Okay, so what are the main ingredients for hash-based proof systems? First, we need linear codes. In general, we are going to use Reed-Solomon codes because there are efficient algorithms for performing the codification. Then we need a collision-resistant hash function, for example, Ketchak, but you can use others such as Poseidon 2. And the idea is that we are going to commit to these code words. And then we need an arithmetization procedure, for example, an algebraic intermediate representation. So the concrete choice of the linear code, the hash function, and the arithmetization will affect the performance and efficiency, determining proof size, whether it's easier to do recursion, prover time, verifier time, okay? Some examples of these proof systems are Starks with Fry, circled Starks, which have shown amazing performance, being able to prove over 500,000 hashes per second for Poseidon 2, Ligero, Breakdown, Bnews that works over binary fields and can be an interesting option to build new zkVMs, and Freyvenius, which also works over binary fields but has smaller proof sizes. So how do we use, for example, Reed-Solomon codes to build a polynomial commitment scheme, which is the main ingredient of many of these proof systems? So the idea is that at some point, what we do is we compile the program we want to prove to a set of polynomial equations that have to be fulfilled, okay? And everything boils down to showing that this polynomial has zeros over some set or it evaluates to some value at some point set, okay? And how we can commit to a polynomial, what we can do is we choose some values, a domain, and what we do is we evaluate that polynomial over that set D. And that is what we call the Reed-Solomon encoding. Typically, we choose a nice domain. And to show that we are not going to change those evaluations, what we do is we build a Merkle tree to commit to those evaluations. And one thing that we need to build these commitment schemes is to have a way of showing that we evaluated this polynomial correctly. And so here, the main ingredient is a theorem, which is the remainder theorem that says that if a polynomial evaluates to the given value at a point, then the polynomial minus the value divided by x minus z should be a polynomial. Okay, and the idea is that we can commit to this polynomial or this function by evaluating over the domain and committing to the Merkle tree. And we could show that this is in fact a polynomial just by giving the coefficients, but that wouldn't make proofs short. We want logarithmically short proofs. So the idea is that we can use the Fry proximity test to do that, which has logarithmic size, okay? That is something you'd like to look when you are trying to learn these proof systems. And well, here is a basic idea of Fry, but what you do basically is divide a polynomial between even and odd parts, and then you do some random folding to reduce the degree of the polynomial by half. This is the same trick you use when you perform the FFT. And here are the two phases of try. You have a commitment where you commit to the code words, and then you let the verifier choose some positions where he wants to query and test whether you are cheating or not, okay? And the interesting thing is you get logarithmically sized proofs, and the prover runs really, really fast. Okay, and here there are like some cool things you can do to have even faster things by leveraging percent primes, but you have to move to a different construction, which is circle Starks. Okay, it's more or less the same as this, but with some tricks. Well, and thank you for listening to me. Happy to answer any questions.
Thank you, Diego.